Hi, this is a one-take recording of a presentation I put together today exploring how we can apply a holographic hyperspace protocol to the problem of climate change, in particular to the problem of managing carbon emissions. So this is the hyperspace protocol. It's pretty straightforward. There's an entity that has a context, and we're going to apply it here. I'm not going to read this bottom paragraph that sort of sets the context for it, and we're just going to get right into it, assuming someone has been exposed to this concept. But briefly, if we're going to model CO2, we need to be able to model theoretically a single molecule relative to all the molecules on the Earth. We need to be able to do it in a protocol that can be transferred in a payment or a smart contract, and that also ties together with the need for like a civic architecture for a smart economy. And those are can be discussed offline out of context. But here right now, basically, we've got this problem where we've got bad accounting. You can't manage what you can't measure, and you need to be able to measure it across scale, or markets aren't going to be able to do their magic to remediate the issue. So diving right in, these codons represent geometric shapes. So I've lifted them out of the alphabet into sort of a geometry, and each one corresponds to a specific geometric shape: tetrahedrons, cubes, octahedrons, dodecahedrons, and then icosahedrons, the E's. And these have mapped kind of broadly speaking to these functional domains of awareness, being, consciousness, decisions, value, intelligence, and trust are the traditional sort of rails that have been analog that are becoming digital. So these things are altogether let systems be smart. We are going to focus today just on the being part, the mapping of complex data into a shared unified model. So data as we see it today is in text and numbers. It's on the left. On the bottom of, I picked out a few numbers. We're not going to worry about all the billions and the billions of carbon that are in the Earth. 99% of it is in the Earth. What we're concerned with is the stuff in the atmosphere. And then there's the parts per million number, which is increasing, and then the ratio of the total carbon in the atmosphere to each individual, which is currently about 4.7 tons per person. Now, right now, I just gave you a bunch of data. It's out there on the internet, and we can assign each ton, we're going to focus on tons, a unique URL, a unique address, and we can then sort of group those and classify those in a stack where we have a reference for trillions and then the billion scale on down to an individual unit. And this could work, but it's going to be overly it's going to require a lot of compression and deduping, and you run into issues right now because this is being done in a lot of different places, and I'm going to argue that adding this geometry to this kind of system will help identify, like right now you can have multiple spreadsheets that have different references to these things, but they don't map together, and that's what this geometry system is going to bring to it, and we're going to dive into that. So coming back out, here's the problem. Everyone's got their own accounting, their own analog context surrounding their spreadsheets, shown there on the right, but there's no accounting for the commons. And so what this system is going to do is create this sort of lattice that allows us to model every single ton of carbon relative to the planetary totals of carbon. So let's get into it. We're going to dive into what this B lattice is. And very simply, in one dimension, it's just a vector. But the vector has to be at in intervals of 45 degrees. So 90 degrees, 135, 45 degrees. In 2 dimensions, you get a square. This is the land of data sheets and workbooks, our stacks of sheets, and that's when we're getting into sort of 3 dimensions, where you see B3, and then B4 is actually a tesseract, which was discovered in 1880 in a book called like A New Era of Thought, right? And so this is a technology which hasn't really been utilized very well, but we're not going to stop at 4 dimensions. We're going to continue on to 5, and then you can see where this goes to 6, 7, and then we're going to stop at 8, right? So we're going to work each A, B, C, D. We're going to leverage 8 coordinates. So like a point in 3 dimensions requires X, Y, Z. In 8 dimensions, there'll be 8. A, B, C, D, E, 1, 6, 7, and 8 to get an address. But just in B, you can have 8 dimensions. And you can take these and you can think of these as kind of like lenses that you can kind of dial to get different subsets. They're each kind of concatenated on each other. You can imagine sort of zooming in and seeing kind of an aggregation probably at the center, or you can sort of pull out and see the details in the big picture. And this is a 2-dimensional slice of an 8-dimensional shape, and there's going to be different sort of resolutions and pixelations of these, but we'll come back to this, but this is kind of a lattice or scaffolding onto which we can paint all that carbon. So let's do it. So we're going to take a single carbon node and we're going to assign it a position in this lattice, and it could start off as a giant sheet of squares which have points of intersections, and those would be the points. Then we can kind of take all the carbon and we can sort of drop them on this grid, and it's pretty straightforward. We could do it in a 2-dimensional plane. And have basically just 2 digits for each. Those digits are going to carry the burden of the work, and we'll come in. There's nuance here, but basically what we want to be able to do is let anyone take a sentence. I'm going to assert any set of random characters up to 256 is enough for the trillions of carbon tons that there are, and you can declare ownership. So right here I've declared ownership of 5 tons of carbon with these random sets of characters, which I've made human readable. They're very friendly. And we can also add regional and industry codes to start associating them with industries as well as geographic regions. Then we can take those now and then tile them on to this lattice where you see the 8-dimensional cube has 256 vertices. Those become sort of the reference points, the oracles onto which we map all these random sort of permutations and freedoms that we have. So we can all create our own identifiers. If there's a collision, this is where we find it in these 6, 7, and 8. That's where the order starts to get enforced. And the way to do that is to sort of this is one way of doing it, and this is kind of fun to talk about. Where on the bottom is a 256 character sentence from Alice in Wonderland. You can take those characters and then map them onto these circles, and that defines one of the points. So each point, in a sense, has a set of these parameters chosen on it on the side that defines where it is. So in this way, you end up with the ability to have infinite variability and different expressions of what you want. To call something, and you can project it into this 8-dimensional space where everything kind of gets deduped and resolved so that we can avoid double spending, and we can prevent greenwashing. And I think that's it. That's my 8-minute presentation on one of the 8 dimensions of the smart 8-fold path for a smart economy. Thanks.